Good morning. I'm going to continue today with my discussion of Lagrangian Mechanics. Call it analytical dynamics if you want. Lagrangian Mechanics is just fine because we're just applying Lagrange's equation to most things. We'll also look at Hamilton's equations. Now yesterday we said that there is a thing called the action. It's a functional. And it's a function of the generalized coordinates qi. I could be anything. I goes from 1, 2, 3, depending on the number of degrees of freedom. Qi dot are their derivatives, okay? Now this action we vary the action using the method of calculus of variations. You don't need to know what that is. This is lecture 5. Lectures 1, 2, and 3 have not been done yet. I know I labelled one 3 last term, but I'm going to make it 4. And what we say is this. If we take an evolving path in qi space and t space, and we can take any path, path 1, path 2, path 3, but we choose a path that is the minimum. The minimum what? The minimum action. The minimum path between t1 and t2. They are the endpoints, right? So we'll choose a geodesic path. That is the shortest distance between the 2 points t1 and t2. We'll make that path a minimum, okay? So that's the way nature does. And Hamilton, his principle says that nature works such that a mechanical system, if it's conservative, we can derive forces from a potential, non-dissipative forces. Okay, so then if that's the case, nature evolves, allows the system to evolve such that this is a minimum. That's Hamilton's principle. So yesterday we talked about Maupertuis, Hamilton, Euler, and Lagrange. We could throw in somebody else in there. Fermat. We'll do that eventually because there are a lot of principles in here, all to do with the way nature works. All right, so the condition that makes this minimum path is given by Lagrange's equation. We set that equal to 0 and we get the path. The path that is a minimum between here and here. And that path actually is the equations of motion. Basically it's just getting back Newton's law, force equals mass times acceleration, right? But we're getting it by a different principle. We're getting it by a principle, whereas this is just a statement. Newton stated this. This is kind of saying why. And also, we can set up the coordinates, general coordinates, to match the system. Now yesterday we looked at a simple pendulum of length L and a mass on a string, swinging. And we chose small oscillations. Okay? Now I can't remember if it's L over G or G over L. I think it's L over G. But you can check the lecture yesterday. And this is the equation of simple harmonic motion when the motion is small. But in general, theta is sine theta, and then the motion may become chaotic. Okay? Now later on we will look at couples systems. We'll take another string of length same L and put another mass on it, and these oscillations will be coupled and they will get much more complicated, right? And we'll look at the normal modes of those swinging masses. Today we'll also look at another coupled oscillations. We're going to look at the problem of masses on a spring. But we're going to fix the endpoints and allow the masses to vibrate, and we're going to say that the spring is going to have constants k all the same, and the masses m1 and m2 are the same. That's what we're going to do. And then we're going to look at constrained motion. We're going to look at a particle moving on a paraboloid. That's what we're doing in this session. Get my clock. So I don't need anything on the board now. Hamilton's principle. Apply Lagrange's equations to enforce it. Lagrange's equation will pick out the geodesic and tell us that the equations of motion are such that the path is a geodesic. Geodesic is the shortest distance between 2 points, and I'm going to talk on geodesics. So this is example 2. So, we'll take the end points and fix them. We will take one mass and the other mass and attach a spring. Now when the masses move, this one will move a distance that way or that way, displaced from equilibrium, okay? Since we're squaring these things, it doesn't matter if we choose the positive or negative sign. We'll call this displacement x1. This mass will move a distance which we will call x2, and these are the generalized coordinates for the system. Once again, mass could move that way from equilibrium. This is the equilibrium point. We don't care. It's going to be squared. The velocity is squared, or the potential part is going to be squared, so we don't even care about putting in a positive or negative sign. So we want to apply Lagrange's equation. For coordinates x1 and x2. We'll do this part first, but first of all we need to write down what the L is. So it's going to be kind of like a half mv squared and a half kx squared. But we need this part first because this is going to be easier. That is the kinetic term. Now the potential term is going to be slightly trickier. Well, we're going to have a term, well, we'll write them all out. Well, we're going to have terms due to each displacement. Half kx1 and a half kx2, the k's are the same. But what happens? Here are the masses. Suppose they both move this way together. There is no stretching of this spring, right? What is the potential energy of the inner spring? Well, there's a difference between the two potential energies. We could work out the potential energy in this spring, and this spring, but that's hard to follow through. I'm just going to say we'll account for a difference because this guy stayed fixed and this guy moved. This one will pick up potential energy, okay? And if you're a student, you don't have to worry about it. Is it going to be x2 minus x1 to be squared or x1 minus x2 to be squared? It doesn't matter. Because when you square this one, you get k over 2 and the cross term. When you square this one, you get similar term. The cross term is the same in both cases. Okay? So that's what we'll leave it as. So that the potential term with a negative sign is going to be this. There's a common factor of k over 2. And we have that, okay? So, we have this, this, and this. So we have 2 of these and 2 of these. Well, the 2's cancel. Now I just want to make sure that I did that correctly. Well, it seems to be okay, I don't know. Okay, so that seems to be okay. So I don't need these scribbly things. Get rid of them. So our Lagrangian becomes that's our Lagrangian. So get your eyes around this stuff because I need room to work and I'm going to apply the equation to our Lagrangian. So for x1, we'll make this x1. And we'll take the derivative this part first of this thing here. And similar, mx2 double dot will be the force for the x2 particle. Now the v. We'll put x1 first in there, and we'll take the derivative, dl by dx1, and here it is down here. I hope I have the sign right. Okay, let's hope the sign is right. Alright, so we're going to get our equations of motion. For x1, here's the first one. Now, we'll swap the minus sign here. So that's the equation motion for the first one. And we set that equal to 0. And for the second one, and we'll swap the minus sign here. And we get that set up. Now let's see if that's correct. Yeah, that's correct. So these are the required equations of motion. that's our equations of motion as requested for coupled masses on a spring. Do we have time to do another one? I'll start doing the next one and perhaps finish it afterwards, but I'll let you get your head around this first. This is example 2. Okay, we're going to stick a particle in a paraboloid, and a paraboloid looks like this. We'll set it up with polar coordinates. Actually, we put in x and y's as well. And we'll set the paraboloid such that that is a case, and we'll consider a height h at some point, and the particle goes around like this. Or it could go like that, but we'll just examine that particular case. We'll convert to polar coordinates. Well, we set it up to be like this. In other words, Z is 1 over a times r squared is going to be this parabola, and it rotates and it becomes a paraboloid because we take for any value of r, there's a corresponding value of z. Okay? So let's see what the equations of motion are going to be. Well, we have delta v. We're going to have a theta because our angle theta will be this one. Polar coordinates. I didn't put in the 0 yet because we have an extra complication in this. We have a constraint, okay? We can write this as follows. We can write the equation of the parabola like that, and let's take the differential. Now we're going to label these things. Actually, I'm going to label it a big A. What are these things? Well, A of theta is a constant. It's going to be A. It's part of the constraint. A of r is negative 2r. It's part of this constraint. Now there is no A of z. Z does not crop up in here, so we can set Z1 equal to 0. However, this the r part, there is an a of r, it is negative 2r. And there is an a of theta. What's a of theta? Nothing. Sorry, my mistake. Nothing for theta. There is something for z. A of z is a. What we do now is we invoke something due to Lagrange. We'll multiply this by a constant, and this one by the same constant, and find what the condition on the constant is that both equations are going to be satisfied. So we have three equations in I guess, three unknowns, but we have an extra one. We have this one too, right? So we have four equations in four unknowns, and this lambda is known as a Lagrange multiplier. Now when z is at some h, let's say this h here, z double dot equals 0. But let's just do that first. Let's just find the equations of motion first. Okay, let's get rid of this. Now that's the velocity, the kinetic part in terms of cylindrical velocities, r dot squared or theta dot squared. It's just like taking the distance element in cylindrical polars and then their derivative. Now the v is just, I think it's mgz actually. Yes, it should be. Now it's just going, v is just mgh. Because h is z. We set the parabola on the origin. Okay, so L equals t minus v. So this equation by the r, let's do that one first. This one here. Okay. And this one here for the theta. The theta one becomes and for the z, actually I'll just work out the derivatives. Minus dl by dr. Okay, minus dl by dr is going to be this one here. Okay, minus dl by d theta. Where is that going to be? Nothing. Minus dl by dz. Just minus mg. Okay? So now we have the three equations. We're going to say that m r squared theta dot, m r squared theta double dot is 0, so m r squared theta dot is a constant. It's going to be the angular momentum. Now I'm running out of time. For this one here, I get that equation, and for this one here, so we have 1, 2, and 3. But don't forget, we also had the constraint, and I've erased it from the board. What was it? Now I forget. It doesn't matter, because I've run out of time. So I will go see next class. Okay, there's a constraint equation, I just forget what it was, but we need then to solve 1, 2, 3, and 4 together to get the 4 unknowns, the lambdas and everything else. Okay, we'll leave it at that.